I am Fokem Bracins, and this is my colleague
Habdelhamid Tissir.
We are students in UniLaSalle Amiens in third year Engineering, Energy and Digital System.
Today we will present our robotic project, which involves the building on our autonomous robots able to efficiently navigate in a maze.
So to begin, we are going to present you the pieces of our robot. So for the different pieces of our robot, we have a chassis that forms the body of our robot, a battery for power supply. We also have two shields for the move, two servo motor, sensor, and a ball ring for the steering. And we also use a shield and a Arduino nano card for our programs. We also add some LED to mark how the robot will turn, and then we will next going to talk you about the assembly of our different parts.
The sensors are connected to the nano card via the power supply, which corresponds to the VIN part. The GND are representing the ground, the SDA is representing the output, while the GPEO is representing the address. Next, the servo motor is connected to the nano card that its 5 volts power supply. The outputs, the pin 5 and the pin 3, are connected to the GND. We also have 3 LEDs connected to the 3 outputs, named the D7 and the D2 and the D4, as well as the ground.
Next, we will move on to the programming part, which consists on code that we develop in different sections.
As we had said, the goal of this project is to make a small robot that can detect obstacles around it and react automatically, moving, turning, and stopping without human control. To do that, I use 3 VL680X distance sensors, 3 LEDs for visual feedback, and 2 servo motors for movement. Each sensor measures the distance near the object, and the Arduino decides how the robot should move in real time. So let's go step by step through the code and understand how everything works. The first section of the code defines how all the components are connected to the Arduino. Each sensor has a special shutdown pin, labeled SHDN1, SHDN2, and SHDN3. The pins let me turn each sensor on or off independently with each importance because all sensors share same default I2C address. To avoid conflict, I assign custom address 0x30, 0x31, and 0x32. This way, each sensor can communicate with the Arduino on the same bus without interfering with the other. I'll also define the LED pins and the servo pins. One servo for the left motor and another for the right. This setup gives me full control over sensing, signaling, and movement. The next part of the code defines several constants that control how the robot behaves. For example, I set detection threshold for each sensor where 50 mm. That means when something comes close than 5 cm, the robot will consider it an obstacle and reach accordingly. Then I create 3 sensor objects, one for each sensor, and 2 servo objects for the left and right weld. When also a small constant named time2, which determines how long the robot should turn when it detects an obstacle. This timing is key to making the robot movement look natural. And next, we have the setup function. The setup function prepares everything before the robot starts moving. First, the code starts the serial communication, which allows me to see distance reading and debug information on the computer. Then, both servos are attached to their respective pins, and all the LED and sensor shutdown pins are set as output. To make sure everything starts clearly, and initially turn all LED and sensor off. After that, each sensor is active one by one. As each sensor is powered on, the Arduino assigns it new address using the small helper function called initialize capteur. This process ensures that all servos, all sensors work together correctly and the same communication line. Finally, a confirmation message appears on the serial monitor, sensor and LED initialize. It is a small but satisfying moment when you know everything is connected properly. Now we reach to hear the program, the loop function. This section runs repeatedly, reading the distance value from all the 3 sensors and deciding how the robot should move. By default, the robot moves forward. Both sensor pins is a way to push the robot straight ahead. Then the robot checks each sensor. The right sensor, sensor 2, detect obstacle on the right side. If something is too close, the robot turns slightly left to avoid it. The right LED lights up to show that the right side has detected something. The left sensor, sensor 3, do the same thing on the other side. If it detects an obstacle, the left LED sign up and the robot turns right. Finally, the front sensor, sensor 1, looks straight ahead. When it sees an obstacle, the robot stops and decides which side to turn, depending on which side it cleared. It compares the left and the right distance and then turns toward the side with more space. This logic makes the robot appear intelligent. It's constantly amazing its surroundings and adjusts its path dynamically. To make debugging easy, the LED and the serial monitor provide constant feedback. When a sensor detects an obstacle, it LED turns on, creating an immediate visual cue. At the same time, the program prints the distance reading and LED on message in the serial monitor. This combination of visual and data feedback helped confirm that the sensors are working properly and that the robot is responding as expected. It also great for demonstration. You can see that on the robot field in real time.
Now we are going to show you how to overview our robot in the maze and how it navigates. As you have seen in the video, our robot is completely entire maze in 48 seconds, following our basic algorithm we are described earlier, and it does completely automatically.
In conclusion, this project combines sensor, servomotor, and smart programming to create a robot able of simple autonomous navigation. It real-world data process. It makes movement decision on its own, which is the foundation of all robotics. This is just the beginning where I could expand the project by adding more ultrasonic module or even a camera to improve obstacle decision. But for now, this setup demonstrates how an Arduino can control movement based on sensor input, creating a smart but efficient autonomous system. Thank you for watching, and I hope you enjoyed this presentation.